All right, today we're going to go over organic chemistry. So the next test is just on organic chemistry, which is chapter 23, which is all about carbon. All right, so carbon. Thing you need to know about carbon is carbon always has 4 bonds in compounds. All right, but the way you can see the 4 bonds are different. You can have a carbon with 4 single bonds. You can have a carbon with a double bond and 2 single bonds. You can have a carbon with 2 double bonds. And you can have a carbon with a triple bond and a single bond. So they all have 4 bonds to carbon. So back in chapter 10, when you have 4 single bonds, you have 4 directions. When you have 4 directions, you have a tetrahedral. And tetrahedral has the hybridization of sp3. So when you have 4 directions, your tetrahedral, your sp3, your bond angle, so your bond angle here is 109.5 degree bond angle. When you have a double bond and 2 single bonds, now you have 3 directions. A double bond is just 1 direction, so this is 3 directions, and that is trigonal planar. And that is in sp2 for the 3 directions, sp2 hybridized carbon. And your bond angle for trigonal planar is 120 degrees. For the next 2, although we're not going to do the 2 double bonds, that's allenes. You're not going to see that. You will definitely see the triple bond. But in either one of these, you have 2 directions. All right, so a triple bond takes up 1 direction, and then the single bond, if you're over here, you got your 2 double bond directions. 2 directions. That is linear. And that is an sp hybridized carbon. And that has a bond angle. Linear is 180 degrees. And so you would say the same about this one, but we're not going to name those types of compounds. The names that we are going to name, if you have all your hydrocarbons are single bonds, you have an alkane. So if you have a hydrocarbon, hydrogens and carbon, all single bonds, you have an alkane. If you have a double bond, then you are an alkene. All right, so again, we're going to be doing a lot of naming, and the letter is very important, alkane. All single bonds, alkene means you have a double bond. And an alkyne ends in YNE, that means you have a carbon-carbon triple bond. All right, so anytime you have an alkene, you have a carbon-carbon double bond. Anytime you have an alkyne, you have a carbon-carbon triple bond. And then again, of course, carbon has to have 4 bonds. So when you put in your other bonds to make sure that your carbon has 4 bonds, your alkene will always look like that. Your alkyne will always look like that. All right, so hydrocarbon simply just means that you only have hydrogens and carbons. No oxygens, no nitrogens, no halogens. All right, so a hydrocarbon means hydrogen and carbon and only hydrogen and carbon. All right, there are 3 types of hydrocarbons that we are going to talk about. Saturated means that they are all single bonds. All right, so this is your alkanes. So your alkanes contain only carbon-carbon single bonds. So alkanes are called saturated hydrocarbons. Unsaturated means that you have at least 1 carbon-carbon double or triple bond. So your unsaturated hydrocarbons are going to be your alkenes and your alkynes. All right. Now we have a special type of hydrocarbon called an aromatic hydrocarbon. And an aromatic hydrocarbon contains a benzene ring. So you need to know what a benzene ring is in order to identify an aromatic hydrocarbon. A benzene ring is a six-membered ring that has alternating single and double bonds. All right, so that is benzene. Now, benzene has resonance, and so you can draw the resonance form where the double bonds alternate on these. So, and these are equal energy resonance structures. And so many times, most of the time, when you find benzene, it has simply a circle in the middle of a six-membered ring. And that is the usual way that you're going to see benzene. And what does that mean? That means you have alternating single and double bonds, but they are going around the ring at all times. So this is your resonance hybrid, simply showing the circle inside of the benzene ring. So if it says benzene, you can draw it with the three double bonds here, the three double bonds here, or the circle in the middle. All of those are acceptable structures for benzene. Aromatic hydrocarbons, because many of these give off nice aromas. Some not so nice, but some of them very nice aromas. All right, so your alkanes, your simplest alkane is the one that has one carbon and all four bonds are bonded to hydrogen. So you're going to have a list of these things that you're going to have to memorize. This is the first one on the list, and you need to know that your CH4 is methane. All right, and so your molecular formula just simply tells you how many carbons and hydrogens you have for a hydrocarbon. Your structural formula is going to actually write out the bonds. And so you have your carbon shown with the four hydrogen bonds. If we have a cycloalkane, that simply means we're going to form a ring. So this one is very important, that is a cycloalkane. All right, so here is a cycloalkane. This is benzene. The circle in the middle makes a tremendous difference. All right, benzene is not a cycloalkane. It is an aromatic hydrocarbon. So the circle in the middle of your six-membered ring, that's when you have benzene, where you can show the alternating double bonds. If there is not a circle, there's not alternating double bonds, then you have an alkane or cycloalkane because it formed a ring. And so when your ring has six members, we know that that is a hexagon, but this is an alkane, so this is a cyclohexane. So cyclohexane is completely different than benzene, but when you're drawing it, it's a subtle difference in the drawing. Make sure that your benzene rings all have the alternating single double bonds or the circle. Your cyclohexane does not have anything in the ring, all single bonds. All right, so this is just showing your sp3, that's tetrahedral, bond angle 109.5. So your alkanes will have a series, right? And the formula for your alkane is CnH2n plus 2. So when we put in 1, we get CH4 because we have 1 carbon and then 2 plus 2, 4 hydrogens. When we put in the number 2, we have C2, then we have H4 plus 2, which is 6. We put in C3 and we get H8. Every time we put in another carbon, we put in another 2 hydrogens. So it keeps going up by CH2. So then you would have C4H10 next, and then C5H12. Every time you increase a carbon, you increase the hydrogens by 2. All right, and so if you are writing these in a straight chain, All right, and so if we had the last one here, C4H10. All right, so if you wrote those in the normal alkane, which means a straight chain of carbons, then you would write it with 4 carbons in a row. Then you would know that you have to put 4 bonds to every carbon. All right, so 4 bonds to every carbon, so you put in then your 10 hydrogens. If you add up all these hydrogens I'm putting in, you will get 10 of them. And that is a butane. So you will have to memorize that 1 carbon is methane, and there's a chart on this as well. 2 carbons is ethane. 3 carbons is propane. 4 carbons is butane. Now, the remaining ones are much easier. So 5, all right, so we already know that 5 is a pentane. Pent is 5. And so C5H12 is going to be pentane. So your C5H12, that in a straight chain is a pentane. And then 6, C6H14, that is your hexane. All right, and so you will need to know your all of your alkanes, the first 4, the ones that are going to be new to you: methane, ethane, propane, butane. Of course, methane is the major component of natural gas, and then followed by your ethane. So methane is mostly natural gas. There's a lot of ethane in natural gas as well. Propane, you have your propane tanks to grill, so you're familiar with propane. Butane is a lighter, and so you're familiar with a butane, but now you have the structures of these things. So methane is 1 carbon, ethane 2 carbons, propane 3 carbons, butane is 4 carbons. And then after that, you will be able to get those answers a lot faster because they are the Greek prefixes that you already have memorized. All right, so it is a homologous series because it keeps going up by a CH2, the same CH2. Each time you add another carbon, you add 2 hydrogens, and so you have a homologous series. And so here is the entire list that you will have to know. Again, the first 4 are going to be new to you. That is methane for 1 carbon, ethane for 2 carbons, propane for 3 carbons, butane for 4. The other ones you would know. 5 carbons is a pentane. 6 carbons is a hexane. 7 carbons is a heptane. 8 carbons is an octane. 9 carbons is a nonane. And 10 carbons is a decane. All right, and so you will need to have this memorized, at least from here to here, memorize it. All right, you don't need to memorize the melting and boiling point, but you need to know that if you have 6 carbons in a row, that is a hexane. 3 carbons in a row, you got a propane. All right, so when we look at methane, it is a gas. All right, so your melting point minus 183. And so it is going to be a gas. Ethane is a gas. Propane is a gas. Butane is a gas. All right, and so to go from a gas to a liquid, here are the temperatures that you would need. All right, that's the boiling point. That is your liquid gas temperature. All right, note butane is all the way up to 0. So your butane will start condensing into a liquid when you hit 0 degrees Celsius. Or if it's under a slight bit of pressure, and that's how the butane lighters work. So it's closed, it's under a pressure there, you release the pressure, the butane comes out, which is flammable. All of your alkanes are flammable. That's what we do with our alkanes, we burn them. There's other things that one other thing we do with them, but mostly we burn them. All right, and so then you get to your pentane, which is a liquid. It will not boil till it hits 36, and then your hexane, your heptane, and the more familiar, your octanes, your 8 carbons, your gasolines. Those are the boiling points there are 126. So, all right, so your octane is your going to be your gasolines, although it is an isomer of octane, which is what we're going to talk about now, and that is isomers. All right, so we had our normal chain. Those are in a straight line. They do not have to go in a straight line. If they do not go into a straight line, then they're going to be called isomers. So if we look at butane, and we have butane that has 4 carbons in a row. Or we could put a carbon, a carbon, a carbon, and then we could put a carbon off of the middle carbon, and we still have 4 carbons, but they do not go in a row. So this would be 1, 2, 3 carbons in a row. This, 1, 2, 3, 4, this is 1, 2, 3 in a row, but another carbon is coming off of carbon number 2. And so these are constitutional isomers. And so you have your butane, which is your normal 4 in a row butane. And then you have an isomer of butane called isobutane. Now to name it correctly, iso is an acceptable name. It is a common name. To name it systematically, you find the longest carbon chain. And in this case, our longest carbon chain is 3 carbons. And so from your list of memorized alkanes, everything here is a single bond alkane, you know that that is a propane. All right, and so that's your base name, 3 carbons in a row. But off of carbon number 2, we have this CH3 group. All right, and so when you have an alkane like CH4, which is methane, if you take off a hydrogen, then it's called an alkyl group. All right, and so if you take off a hydrogen, now you have CH3. Now, alkyl is a group, not a compound. Alkane is a compound. You have 4 bonds to carbon. Your alkyl group has just 3 bonds. It has to attach to something. And so to name it, instead of an ANE group here, we have a YL. So we change the ANE to YL. So this is methyl. So your CH3 is a methyl group. And so off of carbon number 2, you have a methyl group. And so this is called a 2-methyl propane. All right, so you will note that when you have a number and a letter, you always have a dash between a number and a letter. And methyl propane is 1 word. That is not 2 words. It is a 1 word, 2-methyl propane. All right, so when you have a number and a letter, you will put a dash between any number and letter. All right, so if we are going to name our 3 constitutional isomers of pentane, you couldn't just simply say isopentane because there's 2 isomers of pentane. And so you have to give it its systematic name. 5 carbons in a row, that's simply pentane. Now we have 1, 2, 3, 4 carbons in a row, and that's how we get our base name butane. But off of carbon number 2, we have another carbon group. That is our CH3. That is our methyl. So 2 gives us the location. Off of carbon 2, you have a methyl group. So it is 2 dash because it's a number and a letter. 2-methylbutane. All right, and then the last one here, your longest carbon chain is 3 carbons in a row. And so that gives you the base name of a propane. Off of carbon 2, you don't have just 1 methyl, you have 2 methyls. And so you have a dimethyl propane. So you have 2 methyls. All right, if you have 2 methyls, anytime you have the prefix di, you must write 2 numbers, even if it is the same number twice. You would not say 2-dimethylpropane. You have to have 2 numbers when you have the prefix di. So 2,2-dimethylpropane. Note that your numbers, whenever you're writing multiple numbers have a comma between the numbers. 2, 2. Then you have your 2, which is a number, and your D, which is a letter. Numbers and letters you will have a dash. So you have a 2,2 dash dimethyl propane for the name of that isomer. And they are all isomers because if you add all these up, they are all C5H12s. All right, so every time you add them up, you get a C5H12 here and here and here. They have the same molecular formula, but they have a different arrangement. So you have 3 constitutional isomers for your pentane. All right, so this one is interesting. So if we wanted to give the molecular formula, you simply add the number of carbons, 1, 2, 3, 4, 5, 6, 7. So that is a C7. And since there are no double bonds, no triple, everything is a single bond, it is an alkane, you have your 2n plus 2. So it is 16. Or you can count all the blue hydrogens, and you will get 16 of those hydrogens. All right, so write the condensed structural formula. So now is when you're writing your CH3. So the first one is CH3. Then the next one is CH2. And then the next one is a CH. But that CH is bonded to this CH3. So in parentheses, you will write CH3. And that's bonded to a CH. And then that's bonded to 2 CH3. So you have to put CH3 in parentheses sub 2. All right. So that is the condensed structural formula. You can also write it in the stick model. And that is the way that is the easiest way or shortest way. But you have to understand what these things are representing. So this is the way that I would represent that molecule, where this is understood to be a carbon, this is understood to be a carbon, this is understood to be a carbon, this one is a carbon, this one is a carbon, this one is a carbon, and this one is a carbon. All right, so the first one, that's my CH3. That's my CH3. And then the second one, that's my CH2. You have to have 4 bonds to carbon. That means you have to have 2 bonds to H there. And then my third one, that's my CH. I need 1 H because it already has 3 bonds. It just needs 1 more. And that's attached to the CH3. That's why down here I have my CH3. And then the next one in the chain is my CH. This one here also has 3 bonds. It just needs 1 H. And then up and to the left are both CH3s. And so I will use this way to do my condensed structural formulas. All right, now we want to name it. And so if we number the longest carbon chain, we'll go up here, 1, 2, 3, 4, and 5. All right, and so if we number that 1 through 5 that way, we will get the wrong answer for our name. All right, because here would be a group off of carbon 3, we'd have a methyl, and off of carbon 4, we would also have a methyl. But there is no rule that says we have to number from left to right. We can also number from right to left. And that would be a 1, that would be a 2, this would be a 3, this would be a 4, and this would be a 5. So anytime you find the longest carbon chain, you can number it left to right or right to left. The way that the rule states is that you will number it the way that gives you the lowest number for the first substituted group. So if we went from left to right, we don't get a methyl until we hit carbon number 3. If we go from right to left, we hit a methyl at carbon number 2. And so if you went from left to right, you would call it a 3,4 dimethyl. No, because if you went from right to left, you would have a 2,3 dimethyl. Always the lowest numbers possible. So 5 is the longest carbon chain. That is a pentane. And then off of carbon number 2 and off of carbon number 3, so 2, 3, anytime you have more than one number, When you have di, the separation for numbers is a comma, and so then you have a dimethyl pentane. All right, so anytime you have a dimethyl, you have to have two numbers. So you have a 2, 3 dimethyl pentane for the UPAC name, the international name for that compound. So the longest carbon chain, that's your base name, and then the groups that are coming off have to have the smallest number possible. All right, your cycloalkanes. In order to have a cycloalkane, to make a ring, you have to have a minimum of 3 carbons. And so you'd have to have a carbon, and that's bonded to a carbon, bonded to a carbon. In order to get a ring, you would have to have at least 3 carbons. All right, and so that would be then, to give everything 4 bonds, you would have to have 2 H's on each one of these carbons to give all of these carbons 4 bonds. And so that has the general formula of CnH2n, because here we see 3 carbons, 6 hydrogens, yes. C3H6, so you put a 3 in for N, you get 6 for H. All right, and so the way that everyone will write a cycloalkane is in its condensed structural formula, where, of course, if I say to name this, I am not looking for a triangle name. I am looking for a cycloalkane. So 3 is propane, except this is not normal propane of 3 carbons in a row. This is in a ring, which we call cyclo, and so this is then called cyclopropane. And so, of course, if you're going to name a square, the name is not square, it is cyclobutane. Because you have 1, 2, 3, 4 carbons. So it's cyclobutane. All right, and so you have here, they just list a couple more. You got your cyclopropanes, your cyclobutanes, your cyclopentanes, your cyclohexanes. So we kind of did cyclohexane because this one gets confused many times with benzene. So a cyclohexane does not have alternating single and double bonds. But a benzene ring is a 6-membered ring. You put a circle or alternating single and double bonds, and now you have benzene. So anytime you are forming a ring, a circle of carbons, your name is going to be a cyclo, number of carbons. All right, and so everyone will write these in their condensed structural formulas for your cycloalkanes. All right, sources and uses for your alkanes. We get our alkanes from petroleum or crude oil. They have different number of carbons depending on where you're getting your petroleum. Some are 20 to 40 carbons, some are 5 to 20 carbons. When you want your gasolines, you want that to be about 8 carbons, your octanes. But gasoline is not a pure one compound. It's a bunch of different compounds. All right. So your alkanes, so that's what we do with them. We burn them. So the first thing that it says here, reactions of alkanes. We do complete combustion. All right. When you're heating your house with gas, yes, that's natural gas. You're burning your methanes. You're driving your car. You're burning your octanes. All right, so things that we do with our alkanes is we burn them. And then the product of combustion of organics is carbon dioxide and water and, of course, heat. All right, so that's what we do with our alkanes. But if you're doing organic synthesis, there is we're not ever trying to synthesize carbon dioxide. We are trying to synthesize other organic compounds. And so we will do a substitution reaction for our alkanes. And we will do that by using chlorine or bromine. And one of the hydrogens is going to be substituted with a chlorine if we add Cl2 or a bromine if we add Br2. And that is then a substitution reaction. All right, so the simplest one here is our CH4. And we added a Cl2. All right, the easiest way to get to a product is to lasso a compound. You can lasso water many times. In this case, it is HCl. If it was the bromine, you would lasso HBr. All right, and so then your product is, you get that HCl product, and then the remaining part, which is your organic, which is your CH3, bonded to your Cl. So this is your organic product. So whenever you're doing organic synthesis, you don't care about the HCl because that's not organic. You care about the CH3Cl. That is your carbon-containing product. That is your organic product. It lists fluorine here as a reaction. Fluorine usually reacts way too fast. We don't normally use fluorine for this substitution. For this class, it will be exclusively chlorine, which is pretty fast, and bromine, that's pretty slow, but still at a good rate. And then iodine is way too slow. So fluorine's too fast, iodine's too slow. So we're going to stick with the bromine and the chlorine. All right, so you see that we have substituted an H for Cl. So there used to be CH4. It used to be an H here. It has been substituted with a Cl. So that is a substitution reaction. We substituted one thing for another thing. All right, you can lasso HCl a second time if you do it again. You can lasso it a third time if you do it again. And finally a fourth time until you have all of your H's being substituted with chlorines. And that will give you your CCl4. But in organic synthesis, we always want to stop after the addition of one halogen. And then we can do many reactions with that compound. All right, your alkenes and your alkynes. Again, these are called unsaturated because they contain a double or triple bond. If you are an alkene, that means you are going to have a carbon-carbon double bond. And it also means that when we name an alkene, it's going to end in ene. If you have a carbon-carbon triple bond, then you have an alkyne, and the names of those will end in yne. So your alkanes end in ane, your alkenes end in ene, and your alkynes end in yne. All right, your alkene has the same general formula as your cycloalkane, and that is a CnH2n. Your alkenes have an old name called olefins. So someone says olefin, they're talking about an alkene, and you're talking to somebody really old, older than me. I do not call alkenes olefins. I call them alkenes. Now, you can convert your alkenes or your alkynes back to your alkane or into your alkane by doing a catalytic hydrogenation. So the catalyst is normally platinum, so you would have a platinum, and then you would add hydrogen. And so that would add hydrogen across the double bonds for an alkene to make an alkane, or do it twice on your alkyne in order to make your alkane. So hydrogenation is adding hydrogen. Catalytic means you needed to add a catalyst, in this case, a platinum catalyst. All right, now your alkenes have what is called geometric isomerism. You do not have free rotation about a carbon-carbon double bond. You do not rotate a carbon-carbon double bond. And so this makes it possible to have what we're going to call cis and trans isomers. All right. So on the next slide, we're going to see that if you have H's on the same side, all right, and these things just have to be not H. Anything not H. You can put bromine, chlorine, another carbon group. I think they're going to use CH3 and CH3. All right, so you have to have a hydrogen and not another hydrogen on that side. A hydrogen and not another hydrogen on the other side. And then you will have cis-trans isomers. When your H's are on the same side, that will be cis. If I wrote the same compound, But this time I have my H's on opposite sides. Then I have the trans isomer. And since you don't have free rotation of a double bond, in order to rotate a double bond, you got to break the double bond and then rotate and then form that double bond. So that is a reaction. When you are breaking bonds, you're doing a reaction. It does not have free rotation. So you have cis and trans isomers. All right, and it's all about the H's. If the H's are on the same side, both on top or both on bottom, that is cis. When you have one on top, one on bottom, one up, one down, you have trans. So that H going up, that H going down, you have a trans isomer. Now to name this, all right, you got to find your longest carbon chain, 1, 2, 3, and 4. And that's your base name. So that is a butene. Ene, because you have a double bond, not butane. Butane is everything single bond. Butene. Now, in order to get the position of the double bond, you must use the lowest number possible for the first carbon in the carbon-carbon double bond. All right, and so your carbon number 2 is when your double bond starts. All right, and so then this is a 2-butene. So this one is a cis-2-butene. And this one is a trans-2-butene. So they are both 2-butenes. But one has the H's on the same side, and the other one has the H's on opposite sides. Cis is the same side. Trans is the opposite side. All right, and so they have different boiling points, where your cis has a higher boiling point at 3.7 versus the trans has a lower boiling point at 0.9 degrees Celsius. All right, so you can isolate your cis-2-butene, you can isolate your trans-2-butene. They do not freely rotate to the other isomer. Again, H is on the same side is cis. H is on opposite side, that's trans. In order to have geometric isomers, you have to have different groups on the left and different groups on the right. So here is the left side of the double bond. Those two have to be different. Here's the right side. These two have to be different. If you had two H's on one side, you cannot get cis and trans. If you had two methyls on one side, you cannot get cis and trans. If you had two anything the same thing on one side, you do not get geometric isomers. All right, so let's try this one. Draw this one out. We've got, I always start with the double bond. All right, so there is my double bond right here, right here. All right, and then this side has an H and it has a CH3. The other side has an H and it has a CH2, CH3. And so you see that my H's are on the same side. So this is my cis isomer. And then, of course, you can have your trans. So if I want the H to be down here, and then the CH2, CH3 up here, and now I have my trans isomer. And so let's name it. All right, and so we have 1, 2, 3, 4, and 5. All right, I didn't do that on the previous one, but I'll do it quickly here. Where did I number those? Here I numbered them. Anytime you number it from left to right, you could also number it from right to left. 1, 2, 3, 4. For the 2-butene, the lowest number was 2 in either direction. But you should do that every time, because in this case, it's going to be a different number. And so the way it is from left to right, that is a 2. But if I go from right to left, where this is a 1, and this is a 2, and this is a 3, and this is a 4, and this is a 5, my lowest number for the first carbon, this number is a 2, this number is a 3. So 2 is lower than 3. So we want the first carbon of the carbon-carbon double bond to be a 2, because that is lower than the other direction, which would be a 3. All right, and then 5 is a pentene. So this is a cis-2 pentene, ENE, because it has a double bond. It is an alkene. So again, you will not number it 1, 2, 3, 4, 5, because that would be a 3 pentene. That is the wrong answer. It is a 2 pentene, because when you number it the other way, 2 is the number that you get for the first carbon of the double bond. So there's always 2 choices. So you're going to have a 3 or a 2. Always pick the lowest number. All right, so the longest carbon chain is still going to be 5. So you're still going to have a pentene, but it has to be a 2 pentene, not a 3 pentene. Your alkenes will also do oxidation reactions. So if you put some KMNO4, you will see a color change because that is going to do an oxidation of your alkene. Your double bond is reacting. If you had an alkane, there would be no color change and no reaction. So it is a way to determine if you have a saturated or an unsaturated hydrocarbon. All right, so your alkanes did substitution reactions. What you're going to find for your alkenes is they're going to do addition reactions. It is just going to add to its molecular formula. You're going to add things to the double bond. So we're going to add bromine, we're going to add chlorine, and a hydrogenation added hydrogen. Those things to add are easy because you're going to put a bromine on both sides, or you're going to put a chlorine on both sides, you're going to put an H on both sides. If you are adding HBr or HCl, which is also very common, now it matters. Is the H going to the left? Is the Br going to the left? Is the H going to the right? Which one's going to the right? Which one's going to the left? So it matters. When you're adding the same thing, you're putting the same thing on each side of your double bond, and it doesn't matter. All right, so if we look at a propene, and interesting that it does not label it as a 1-propene. If you put 1-propene, I would not count that wrong. But since there's no such thing as a 2-propene, because if you numbered it incorrectly and you said this is a 2-propene, then that is wrong. Because one direction your number is 1, the other direction your number is 2. 1 is the lower number. There's no such thing as a 2-propene, so you don't have to put in the number 1. Unfortunately, that is not the same for butene. So here, if you don't put 1-butene, it is wrong, because if you just said butene, it could have been 1-butene or it could have been 2-butene. All right, so butene has both a 1 and a 2. And so you have to say whether it's 1 or if it's 2. With propene, there's no such thing as a 2, and so you don't have to put the 1. All right, I would recommend go ahead and putting the 1. If it is me grading it, that is fine. I do not take off for a number that doesn't have to be there, that's there. However, if you called this butene, it would be wrong, because without the 1 here, I wouldn't know if you're talking about this butene or this butene. All right, so they messed up this slide a little bit, because all you're going to do is this double bond is now going to be a bond to an Br on this side and the other side. So you're going to have a CH3, and now it's going to be a single bond, and then we bond it to a Br and a Br. And to name this, we want the lowest numbers possible. So I'm going to start with the bromine on number 1. I'm not going to start over here where there's no bromine. And so I have a 1, 2. All right, and now I have 2 bromine. So that is a dibromo. And then the longest carbon chain is 3. All right, and so that is a propane. There's no double bond anymore. It's all single bonds. And so now it is a propane. Anytime you do an addition reaction, Now you don't have any double bond. You have all single bonds. It is no longer a propene, it is a propane. All right, so here is what happens when you add an unsymmetrical, so HBr. So again, you could put the H on this side, you could put the Br on this side, or you could put the H on this side and the Br on this side, and it does matter. So the rule is, Markovnikov's rule says the H is going to go to the side that has the most carbon-hydrogen bonds. All right, so the H goes to the side with the most carbon-hydrogen bonds. So this carbon has one carbon-hydrogen bond, and it has a carbon bonded to the methyl. On the other side, it has two carbon-hydrogen bonds. All right, so this is 2 bonds to hydrogen. This is 1 bond to hydrogen. CH3 is not 3 bonds to hydrogen. Methyl is methyl. So this carbon is bonded to 1 H and a methyl. This carbon is bonded to 2 H's. And so H goes to the side with the most H's. And the most H's you can have is 2. Maximum is 2, because when you have a carbon-carbon double bond, that means you have 2 other things. So if they're both H's, that's as most H's that you can have. So you're either going to have 1 H here, 2 H's, or you would have 0 H's. If I put 2 CH3s up here, then there's no H's on the left. But the H is going to go to the side with the most carbon-hydrogen bonds. All right, and so here is our product. This is the product. This is not the product. All right, and so your only product is a 2-bromopropane. You do not get 1-bromopropane. Markovnikov's rule. H goes to the side with the most H's. All right, and so you might get a little bit of the other product, but by far the major product is the Markovnikov product, which is you get from the Markovnikov rule. All right, so is the one obtained when the hydrogen atom of the reagent adds to the carbon atom of the double bond that has the greater number of hydrogen atoms attached to it. So the H goes to the side with the most H's, and that's why the major product is a 2-bromopropane. All right, so if we look at this example, all right, first we want to number it. So there's 1, 2, 3, 4, or 1, 2, 3, and 4. And so when we name it, either way we name it, the lowest number that we get for the carbon-carbon double bond is a 2. And so we have a 2-butene. All right, 4 carbons would be butane, but you have a double bond, so it is butene. And the first carbon, the carbon that starts the double bond is a 2, whether you number it left to right or right to left. Now it matters. So we either put a 2-methyl-2-butene, or we would put a 3-methyl-2-butene. The rule is the lowest numbers possible. And so 2, of course, is lower than 3. And so this is a 2-methyl-2-butene. Now you would say, what about cis and trans? It's an alkene. All right, so if we look at this carbon-carbon double bond, you see that on this side, it is a methyl and a methyl. If you have the same group on one side or the other side, you will have no cis-trans isomers. All right, so you have the same group on one side, so you cannot have any cis-trans isomers. So this one does not have any cis-trans isomers. All right, so you have 2-methyl-2-butene. Now we're going to add the HCl. So the one on the left has no bonds to hydrogen. The one on the right has 1 bond to hydrogen. 0 bonds to hydrogen, 1 bond to hydrogen. And so the H is going to go to the side that has the most bonds to hydrogen, and then the Cl is going to go to the other side. And so we have our CH3, C and then CH3, all right, and then a C with an H and a CH3. And so since this carbon has an H, that's where the H is going to go. And this one does not have any H's, that's where the Cl is going to go. And so when we name this, we have 1, 2, 3, 4. So we have a butane, no more double bond, butane. And off of carbon 2, we have a 2-chloro, and we have a 2-methyl. So that is a 2-chloro-2-methyl-butane. And they always go in alphabetical order. C must come before M. You can disregard the numbers. It doesn't matter if this number was a 3. For example, if I wanted to name something that had a methyl group here and then a chlorine group here, I would have 5 carbons now. All right, so this is 5 carbons. That would be a pentane. And then off of carbon 2, I have methyl. Off of carbon 3, I have a chlorine. But the alphabetical order is what dominates. This is a 3-chloro, 2-methyl, pentane. All right, so it is not about number order when you're naming it. It is about an alphabetical. The chloro comes first because it is alphabetically first. Methyl then comes second. All right, so the alphabetical order is going to dominate. All right, we will pick up there next time.